Imagine for a second you're in total darkness. You're trying to feel the difference between, say, a concrete pillar and a piece of soft velvet.
No sight to guide you at all.
Exactly. But your brain, it just instantly knows what those materials are. That immediate, intimate connection to the world, that's all thanks to our sense of touch, or somatosensation.
And you could argue it's our most fundamental sense. I mean, think about it. Vision and hearing are localized to single organs.
Right, your eyes and ears.
But touch is this truly distributed sensor array. It's everywhere, all over your body. And our sources today show it's so precise it can distinguish between surfaces that differ by, and this is wild, a single layer of atoms.
Welcome to the Deep Dive. Today we're taking a huge stack of literature covering everything from molecular biology to robotics, and we're going to distill the absolute most fascinating parts for you.
Our mission today is to really unpack the science of how we feel the world, right down to the tiny molecular switch that registers a single tap. We're looking at the biological hardware, the cognitive software, and how these incredible discoveries, especially the Nobel Prize-winning work on the piezo2 ion channel, are leading to things like artificial skin.
Okay, let's start with that biological hardware. It's so easy to think of our skin as just one big pressure sensor.
Right, like a single sheet of material.
But it's not.
Yeah.
Especially on the fingertips, the non-hairy skin. It's this incredibly sophisticated array of specialized data collectors. They're called mechanoreceptors.
And they basically function as a set of mechanical filters. Scientists classify them into four main types, mostly based on how quickly they adapt to something touching you.
Adapt. What do you mean by that?
So do they fire a signal rapidly when a touch begins and then just go silent?
Okay.
Those are the rapidly adapting, or RA, receptors.
Right.
Or do they keep firing the whole time you're applying pressure?
Yeah.
That's the slowly adapting, or SA, receptors.
Got it. So if I'm lightly stroking my phone screen right now, which ones are firing off the fastest?
That would be your Meissner corpuscle. They're an RA type, optimized for low frequencies, maybe 2 to 40 hertz.
And what's their main job?
Their whole function is detecting flutter and motion. Think of them as crucial for all those little micro adjustments you make, like when you're about to drop a wet glass. It's your quick response alarm.
Okay, so that handles slip detection. What about sustained contact? The thing that gives us the actual, fine grain of a texture.
That's the job of the Merkel cell neurite complex. They're the SA type, the slow ones. They respond to very low frequencies and they are the true map makers of the hand.
This is where we get the high-res data.
The highest spatial resolution we have. A truly remarkable 0.5 millimeter acuity on the fingertips. That's what lets you perceive form and all that fine texture.
So we have fine detail and we have slip detection. But what about the sense of stretch? Or, the overall shape of the object I'm holding. We need something that tracks tension, not just surface detail.
And that's where the Ruffini endings come in. They're also slowly adapting, like the Merkel cells, but their whole thing is responding to the stretching of the skin.
Like when I open my hand wide.
Exactly, or when you grasp a big object. They help your brain understand your hand's shape and the direction of motion. It's the system that's constantly updating your brain on your hand's posture.
This is incredible. It's like 4 different data streams being collected all at once. But now we have to talk about the superstar of vibration detection, the Pacinian corpuscle.
Ah, yes, the Pacinian corpuscle. This is the extreme fast responder. We're talking high frequencies, often peaking around 250 hertz, but they can go up to 500.
And these are the sensors that let you use a tool, right? Like you can feel what a shovel is doing in the dirt.
Precisely. Or a surgical instrument. You feel what's happening at the working end.
Okay, so we know it detects high vibration. But what's the secret? How does it completely ignore just a steady, static press?
That's the structural marvel. It has this signature onion-like capsule made of all these concentric layers. Like an actual onion.
Like an actual onion. And that capsule acts as a high-pass mechanical filter. The fluid inside those layers just redistributes if pressure is applied slowly.
So the static touch never even reaches the nerve ending.
It never gets to the core. Only quick, high-frequency transients, those intense vibrations, can get through that mechanical shielding and trigger a signal. It's basically a built-in physical noise-canceling system for low-frequency junk.
That is just incredible. The body is filtering the world before the signal even becomes electrical.
Yeah.
And that electrical conversion, how physical force actually turns into a nerve impulse. That was a huge mystery until very recently.
It was the black box. And this brings us to the molecular level. This is the piezo revolution.
Right, the discovery of the piezo 1 and piezo 2 ion channels. This is what won the Nobel Prize in 2021.
It is. It provided that long sought-after molecular transistor for the whole touch circuit.
So how does it work? How does pure physical force instantly become an electrical signal? It's a literal mechanical switch, not some slower chemical reaction, right? That's exactly right. Piezo channels are these massive proteins sitting in the cell membrane. And what cryo-electron microscopy suggests is this lever arm
A
mechanism.
lever arm.
Yeah. When physical force stretches the cell membrane, the protein's outer blades, they flatten out. This movement applies a mechanical torque to a beam inside the cell.
Which then does what?
It physically pulls open the central ion pore.
Like opening a massive trapdoor.
It's exactly like that. And once that pore is open, positive ions like calcium and sodium rush in, and bam, you get an electrical signal. This direct mechanical gating is why our sense of touch feels instantaneous.
So the hardware detects the signal, turns it into electricity, but then the brain's software has to process it into a feeling. And the sources here point out that the nervous system uses two totally separate pathways for this.
This is one of the most important takeaways. Touch has this dual nature. You have the objective, analytical touch, and then you have the emotional, subjective touch.
Let's start with the objective part, discriminative touch.
Discriminative touch, the what and where of it all, is about speed and precision. The signals travel through these big, fast afibers up the dorsal column medial lemniscus pathway.
That's a mouthful.
It is, but think of it as a neural superhighway. It's a specific bundle of nerves moving at lightning speed, 35 to 75 meters per second, shooting straight to the primary somatosensory cortex, S1.
And that tells you definitively what you touched and exactly where.
Exactly. But then you have the other side of it, the touch that makes you feel safe or loved or comforted, the emotional connection.
That's effective touch.
Right. And this uses a completely separate network of thin, unmyelinated fibers called C-tactile efferents. These are slow, they aren't for discrimination, but they are highly tuned. They respond best to slow, gentle stroking.
At skin temperature, right?
At about 1 to 10 centimeters per second at skin temperature. And their destination in the brain is absolutely key.
Because they don't go to that S1 cortex.
Crucially, no. These signals bypass S1 entirely, and they project to the posterior insula. That's the brain's center for interoception, for mapping your body's internal state. This is the physiological link between a gentle hug and feeling okay. It's a dedicated neural system for social bonding.
So when those fast signals do reach S1, we run into the homunculus, that famous, really distorted body map. Looks like something from a horror movie, with these gigantic hands and lips. Why is our brain's map so weirdly skewed?
That distortion is called cortical magnification, and it's essential for how we function. The hands and lips get a massively disproportionate amount of neural real estate.
Like 50% sometimes.
Sometimes up to half of the entire tissue for somatosensation. And that extreme allocation of pixels, if you will, to the fingertips is precisely why our spatial acuity is highest there. You can distinguish two separate points just 1 or 2 millimeters apart.
So the brain is just allocating massive computational power to the areas that need the most detailed data for, manipulation and communication.
That's exactly it. And the truly amazing part is that the brain software is never static. It's constantly being rewritten based on your experience.
The plasticity is just stunning. I'm thinking of people who are congenitally blind.
A perfect example. In those individuals, the part of the brain that normally processes vision, the visual cortex, or V1, it gets colonized by touch input.
Colonized.
Yeah. fMRI studies show that when they read Braille, their V1 lights up. The visual processing center has been completely repurposed for a high-acuity touch task. It's this remarkable neural reorganization.
And our sense of our own body is so constructed by the brain that it can be instantly tricked, like in the famous rubber hand illusion.
Oh, that illusion is amazing. It shows just how fragile our sense of body ownership really is. You hide someone's real hand, and then you synchronously stroke a visible fake hand and their hidden real hand.
And eventually.
Eventually, the person starts to feel the touch as if it's originating on the fake hand. The brain constructs ownership by integrating vision, touch, and proprioception. And it trusts the visual input so much that it just rewrites the physical location of the sensation.
Wow. So this human hand system with these 4 receptor types, it's the ultimate generalist tool. It's fantastic. But when we look at the animal kingdom, The sources are full of these hyper-specialized sensors.
That's a great way to put it. The human system is a wide bandwidth array. It covers a lot of bases. The animal specialists, though, are high-gain, narrow bandwidth sensors. They are optimized to do one thing perfectly.
Okay, let's talk about some of these specialist superpowers. We have to start with a bizarre star-nosed mole.
The mole's Eimer's organ. It is an absolutely extreme example of evolutionary tuning. It has this tactile fovea on its 11th appendage.
A tactile fovea like the fovea in our eyes for sharp vision.
Precisely. And get this, it packs 25,000 sensors into roughly 1 square centimeter.
Wait, 25,000? In 1 centimeter. That's more than the entire surface of a human hand.
It is. And that specialization translates into record-breaking speed. It can identify and eat prey in just 8 milliseconds.
8 milliseconds. That's faster than a blink.
It is the fastest known mammalian foraging behavior. And to handle that data, that tiny sensory appendage takes up a full quarter of its entire somatosensory cortex.
Then you have something completely different like the harbor seal's whiskers, which do something called hydrodynamic imaging. Sounds like something out of Star Trek.
It's a genius mechanical solution. The whiskers have this very distinctive, undulating, twisted shape.
And that shape is the key.
It is. It cancels out the whisker's own vibration from moving through the water, which gives it a phenomenal signal-to-noise ratio. It works like a high-end noise-canceling microphone, but for water motion.
Allowing it to do what exactly?
Yeah. It allows the seal to track a fish's wake 30 seconds after the fish has already passed by, detecting water flows of less than a single millimeter per second. It's like Daredevil sonar sense, but for tracking turbulence.
And then, scaling way down, we have the Cuponea spider using its own exoskeleton to tune its sensitivity.
Yeah, the spider uses these structures, called slit sensilla, to detect tiny flexes on its shell as small as 1 nanometer.
1 nanometer, that's atomic scale.
It is, and here's the trick. The spider's posture, how it stands, applies a pre-stress to those slits, which mechanically tunes their sensitivity. It's like having a variable gain amplifier built right into your body.
So we've got all these amazing specialized solutions, but the experts found a really interesting convergence when they compared rats and humans side by side, specifically on how we perceive texture.
It's all about temporal frequency. It's not just the spatial arrangement of bumps.
So how we move our hands matters.
It's everything. Whether you look at a rat whisking its vibrissae at 5 to 25 hertz or a human instinctively scanning a surface at 5 to 15 centimeters per second, both actions are optimized to induce vibrations.
And those vibrations match the sweet spot of our main sensors.
They match the resonance frequency of their key sensors. Pacinian corpuscles for us, other receptors for rats. Both species landed on the exact same computational strategy. Texture equals temporal frequency.
Even the piezo channel itself gets adapted for these different needs.
Absolutely. In mice and humans, our piezo-2 is fast inactivating. It shuts down quickly, which is perfect for detecting rapid vibrations. But ducks, which probe around in wet mud for food, have a piezo-2 variant with prolonged inactivation.
So their channels stay open longer.
Right. It allows the channel to stay open during sustained pressure, optimizing them for continuous force detection like feeling the stickiness of mud instead of just quick impacts.
This amazing comparative study isn't just for zoologists. It's literally a blueprint for engineers building the next generation of soft robotics and prosthetics. Electronic skin or e-skin.
Yeah, engineers are moving way past simple on-off pressure switches. They're trying to mimic the dynamic, filtering nature of our own receptors.
So how do you mimic something like a Pacinian corpuscle, which only cares about the start and stop of a touch?
Well, one really clever way is using triboelectric nanogenerators, or TENS.
TENGs.
These are self-powered sensors that use static charge, the same thing that makes a balloon stick to a wall. They only generate a voltage spike during dynamic contact, the touch and the release, and they are completely silent during a static press. So they perfectly mimic those RA receptors.
And the spider's extreme sensitivity is also inspiring new materials.
Oh, yeah. The microcrack idea is key. Engineers use these films where resistance changes under pressure, but they pre-crack the conductive coating on top.
They break it on purpose.
They break it on purpose. So when pressure is applied, those tiny microcracks widen, and that drastically changes the resistance. It's a way to mimic that high sensitivity and variable gain of the spider's sensilla.
But the real leap forward, it seems, is making this artificial skin communicate like a nervous system, sending spikes, not just constant data streams.
That's the whole field of spiking neural networks and neuromorphic systems. Recent e-skins integrate sensors with components like memristors to convert pressure magnitude directly into a spike frequency. This rate coding is exactly how our nervous system communicates, allowing for super efficient data transmission.
Okay, so last question on this. What's the biggest technological hurdle for these complex e-skins right now?
The biggest hurdle is the classic decoupling problem, trying to distinguish pressure from temperature.
Because heat can interfere with the pressure signal.
Exactly, that's pyroelectric interference. But engineers are solving this. They're using specific materials and analyzing the signal's steady component, which is usually pressure, versus its alternating component, which is often a rapid thermal change. It's how they're finally mimicking the dual sensory input found in our own skin.
All right, we've synthesized this huge deep dive into the sense that really permeates everything we do. Let's quickly summarize the three biggest takeaways for you, the listener.
First, remember the molecular switch. Touch operates via the piezo ion channel, a Nobel Prize-winning discovery that acts as a direct mechanical lever arm in the cell, physically converting force to electricity in milliseconds.
Second, the dual system. Touch isn't just about fast, objective spatial discrimination. It's just as much about emotional well-being thanks to those separate C-tactile fibers that route slower, comforting signals straight to the insula.
And third, the lesson of the specialist versus the generalist. While the human hand is this versatile four-receptor array, animals like the mole and the seal show us what hyper-specialized sensors can do, especially when they use active sensing strategies. That frequency code for texture, which is now a crucial blueprint for engineers building the next generation of electronic skin.
We hope this deep dive into the secret life of touch has been enlightening and gives you a new appreciation for the sensors covering your entire body.
So here's a final thought to leave you with. If our current prosthetic technology is based on replicating the generalist human hand, how might integrating these hyper-specialized sensors, like the seal's hydrodynamic whisker or the spider's nanoscale strain detector, change how we interact with the physical and even the digital world? That's something to ponder.
Thanks for joining us, and we'll catch you on the next deep dive.